Boyle's law is an expression of the inverse relationship existing between the volume occupied by a gas and the external pressure exerted upon that gas. In this animation, increases in pressure are represented by additional green weights on the top of the piston. Please note that as the number of weights increases, the volume of the gas decreases. But more importantly, I want you to notice that all of this occurs at a constant temperature. For Boyle's law to be true, temperature has to be held constant. But with Charles' law, it's the pressure that has to be held constant. Remember, Charles' law is an expression of the direct mathematical relationship between the Kelvin temperature of a gas and its volume. But what about on those occasions when everything changes? And by everything, I mean both the pressure and the temperature of a gas. When both of those change at the same time, what then? The solution to this dilemma is the combined gas law, which is simply Boyle's and Charles' laws combined. The equation appears on the far right there. V1 P1 over T1 equals V2 P2 over T2. Before we attempt to work a problem involving the use of the combined gas law, I need to make you aware of a set of conditions known as standard temperature and pressure. And that phrase is abbreviated STP. In order for us to make legitimate comparisons of gases, it's been determined that we'll compare them at a specific temperature and pressure. And the temperature, standard temperature, is 273 Kelvin. Standard pressure is 1 atmosphere or its equivalent, which means it could be 760 millimeters of mercury or 101.325 kilopascals. Many times when we are working a problem requiring the use of the combined gas law, we'll be told the initial volume, temperature, and pressure of the gas. And then typically we'll be asked to find the new volume at STP, meaning at standard temperature and pressure. Here's our first sample problem involving use of the combined gas law. It reads as follows. The best corals are at a depth of approximately 10 meters. Suppose you decide to take a deep breath and dive to investigate them. At the surface, your lung volume is 2.4 liters, the air temperature is 32 degrees Celsius, and the pressure is 101.3 kilopascals. At 10 meters, the temperature is 21 degrees Celsius and the pressure is 141.2 kilopascals. What is your lung volume at 10 meters? Following our normal routine, let's begin by identifying our given information. The first volume we're given is 2.4 liters, that's V1. We're told the temperature at the start of the problem is 32 degrees Celsius, that's T1. And our initial pressure is 101.3 kilopascals. That's P1. In addition, we'll need to convert that temperature of 32 degrees Celsius to Kelvin. The problem then tells us that once we dive down the 10 meters, we're going to experience a temperature of 21 degrees Celsius, that's T2, and a pressure of 141.2 kilopascals, that's P2. We'll also need to convert T2, 21 degrees Celsius, to Kelvin before we can solve the problem. The standard form of the combined gas law reads as follows. V1 P1 over T1 equals V2 P2 over T2. Now we're going to rearrange this equation so that we can solve for V2. In order to do that, V2 has to be in the numerator and it has to be by itself on one side of the equation. At this point, it's simply a matter of substitution. Into our numerator, we insert 294 Kelvin for T2, V1, 2.4 liters, and P1, 101.3 kilopascals. Into the denominator, we insert P2, 141.2 kilopascals, and T1, which is 305 Kelvin. And once we complete our calculator work, we obtain a value of 1.66 liters for V2. Remember, we're going to report our answers with 3 significant figures and in scientific notation. Here's our second combined gas law sample problem. A sample of methane that initially occupies 950.0 milliliters at 300.0 kilopascals and 450.0 Kelvin is compressed to a volume of 700.0 milliliters. To what Celsius temperature must the gas be cooled to lower the pressure of the gas to 200.0 kilopascals? 950.0 milliliters is V1, 300.0 kilopascals is P1, and 450.0 Kelvin, that's T1. V2 is 700.0 milliliters, 200.0 kilopascals is P2, and we're looking for T2. Ultimately, we want to express it in Celsius degrees. Once again, the standard form of the combined gas law is V1 P1 over T1 equals V2 P2 over T2. What we need to do now is to rearrange this equation so that we can solve for T2. In order to do that, T2 must be in the numerator and it must be isolated on one side of the equation. Now that we've rearranged the equation, the only thing that remains is to do the substitution and calculator work. V2, well, that's 700.0 milliliters. P2, that's 200.0 kilopascals. T1, 450.0 Kelvin. All of that over V1, which is 950.0 milliliters, and P1, which is 300.0 kilopascals. And this substitution will yield a Kelvin temperature of 221. But remember, this problem asks us for a Celsius temperature. So we've got to subtract 273 to make that conversion. And when we do, we come out with a Celsius temperature of negative 51.9 degrees.
Bye-bye, boys.
Have fun storming the castle.
Think it'll work?
It would take a miracle.
Bye-bye.